Right. Thank you for the opportunity. By way of introduction, I'm George Magklaras. I'm an IT systems practitioner and InfoSec researcher. So I spend half of my time operating life science and healthcare computing infrastructures at the University of Oslo. The rest of the time, I'm a consultant for a small company that focuses on cybersecurity. So I've been involved together with Lucia here, security auditing the Norwegian contact tracing application, Smith Desktop, for a private consortium. And that's the angle of my talk today. So I'm going to be doing the presentation today. Now, while this slide displays the structure of the talk, I should really state that my main goal is to raise awareness of the challenges that we face when we make digital contact tracing applications. While most of you have an idea that your smartphone is using Bluetooth proximity data and GPS coordinates to send data about who you meet and how long you meet them for, the message I'm really trying to relay is that today's solutions are incredibly rushed. They have not been audited extensively, and they can, so to speak, open a can of worms if they are used on a massive scale. So before we get into details, just a very short introduction on what is contact tracing in a general non-digital sense. And starting from the left of the slide here, from node number 1, colored in red, this node represents the index case, which is really the terminology for a confirmed COVID-19 case. And before this is confirmed, it's reasonable to assume that the index case is going around meeting other people that are referred to as contacts. And recursively, the contacts themselves meet other contacts. So we have generations of contacts marked with different colors, purple, blue, and green here. The idea is, of course, that we get hold of these contacts, we isolate them, test them, and treat them if necessary, with the goal to limit the spread of the disease. So that's the general idea with non-digital contact tracing. So the rationale behind digital contact tracing is that the whole manual contact tracing business takes time and resources. And experience shows that one major constraint in a highly contagious epidemic are human resources, because they are few, they get tired, and they, especially in countries that are densely populated, so think of China, I don't know, India, Mexico, the health system gets easily strained. So under these circumstances, the ubiquitous nature of a smartphone can add speed, lower the resource requirements in tracking down the contacts, and that's be of great help. Both methods, of course, have their own margins of error, but the speed of the smartphone is the main factor here. And one last point of this slide is that whatever investment the society makes into perfecting a contact tracing solution, it predated and it will surpass the COVID-19 epidemic, because unfortunately there will be others. At least that's what the experts agree on. So the technology is reusable. So the smartphone contact tracing makes use of the Bluetooth proximity data. And the goal is to measure how close and how long we come together. So every time you go around with your contact tracing application active in your smartphone, your phone will sense other smartphones around by intercepting what we call Bluetooth LE beacons. And these beacons transmit, amongst other things, anonymous ephemeral identifiers. That's how your phone records whoever you come in close contact with. And you might not know the identity or the phone number of this person, but you do know the distinct phone ID. So starting from the left here, if the person, we have two persons, A and B, and they go around in the daily business exchanging anonymous IDs. And unfortunately, the girl here, person A, becomes infected with COVID-19. So her status gets updated, and there are two possible paths now. If we go down the centralized path, if the solution is centralized, a central server shall receive the status update, process the proximity data, and then locate all relevant contacts and send alerts to them. If, on the other hand, the solution is decentralized, the interception of contacts is not exclusively done on a central database, but it's done on a more distributed and privacy-aware manner. But either way, all the contacts will get an alert. Now, most modern solutions today tend to follow a decentralized model, and this has pros and cons, but that's the general idea. So, given the fact that we face an emergency, a number of countries have rolled out their own implementations early. You can see them on the right here. So Australia, China, India, Israel, Norway, of course, Singapore, and South Korea. This is by no means an exhaustive list. It's just drawn out of collaborations and comparisons we made in the process of auditing the Norwegian implementation. And however, I would characterize the global response as lukewarm at best, because as you can see from the left here on the map, a rather large part of the world has so far seen limited adoption of digital contact tracing. You have, for example, North and Central America here. You have the Australian continent, and you have notably large countries in Europe, like Germany and Spain, doing limited contact tracing. A substantial portion of South America, is doing no contact tracing at all. That's not very reassuring. So, given the emergency, the reason, of course, that we see this lukewarm response is all the problems that we have with these early implementations. What are those problems? Well, they roughly boil down to the reliability of the collected data, the extent to which these applications increase the attack vector of the smartphone, whether they violate our privacy or not, and whether the collected data are managed in a responsible manner. So I'll start now with the main part of the talk. This was a small introduction, and let's take a look at the low energy variant of Bluetooth called Bluetooth Low Energy, or BLE. Bravo Lima Echo. The Bluetooth specification is a very large and complex one, but we'll see how the use of technology, the slide here, presents certain challenges for the accuracy, anonymity, and device security. So BLE is the technology component responsible for proximity sensing. So you might recall from the previous slides that we're interested to know for how long and for how close we get to each other. How long is not a problem. All mobile phones have rather accurate timers. The problem is the how close. So if we have the iOS device here on the center, how does this device know when it intercepts the beacon from the little phone on the right here, how far the other phone is? The graph on the left here shows an ideal curve, and it shows the answer. And the principle here is that in radio frequency engineering, the more we move away from a transmitting device, the less the power will be that we are going to sense from the transmitter on the receiver end. So the more mathematically astute amongst you will actually realize that this is an inverse square law relationship. So power is equal to P0, the sensed power, over the the square of r, which is the distance. But this is the theory, and of course theories assume ideal conditions. In practice, how sensitive is the measurement of power at the receiver end is really a fraction of, is actually a function of noise, and the picture is more complex. So to normalize these inaccuracies, BLE uses something that they call the RSSI. And the RSSI, in plain terms, is really a logarithmic relationship that helps us estimate distance. It's a received signal strength indication. And if you look on the table on the right here, you'll see that on the basis of how much power we sense on the receiver, we estimate a distance. However, this table also tells you that the smaller the power, the sensed power, the greatest the statistical error between the estimated distance from RSSI and what the real distance is. So let's say that we have an RSSI value of minus 73.1 dBm, then the estimated distance is 5.6 meters, and then that could really be 3 meters away, or it could be really something between 7.5 or even 8 meters away. So there's a huge margin of error here. So to further prove this and attempt to calibrate the different smartphone chipsets to reduce these errors, various contact tracing application teams around the world followed protocols that detect the differences in ideal conditions. So they took many smartphone models, placed them into what you see on the left here in the picture. This is a picture of an anechoic chamber, and it's a very pristine environment to make RF measurements. And they place the phones, all these phones, in a predetermined distance from a transmitter, in this particular case, 2 meters. And the graph on the right here shows the measured RSSI values in dBm for 18 mobile phones. As you can see, there are huge discrepancies. So in plain English, this means that BLE proximity sensing can be incredibly unreliable, especially in real-world non-ideal conditions, filling up the collected data set with false positives and false negatives. As we speak, there are, of course, engineering efforts to calibrate and resolve these issues, but as far as I know, they haven't been tested at scale, and therefore they remain unproven. So this means that a large portion of this data that collected by Bluetooth proximity sensing is unreliable. And that's the end of the story, really. What about anonymity? So in terms of the anonymity of the BLE identifiers, this slide contains a lot of technical info. You can see here on the left the PDU, what we call the beacon PDU format with the header. But what I want you to keep from this slide, as time is of essence right now, is that as part of the payload, some phones might actually transmit more information than you would care to find. So for example, some phones wrap these ephemeral anonymous identifiers with specific manufacturing data, data for the accessories that you might be using with the phone. So say, for example, that you have your contact tracing application on, but you're using a super duper wireless data set, headset, for example, and someone can track you. They can see that you're wearing this data set amongst many people. And unfortunately, this can form the basis for a linkage attack, an identification attack. So the bottom line here is that, again, depending on how well equipped is your adversary and whether they have a visual contact and a sophisticated way to record the beacon traffic, they can actually identify you. So the anonymizations and randomizations of the addresses, of the BLE addresses, may not be so anonymous after all. And on top of that, you have another threat that's called, that really concerns older smartphones, called roost-snaffing attacks. This is a type of attack used to hijack aspects of your Bluetooth connection and can lead to information loss. So an important catalyst here is also the BLE range, which for the advertising beacons can extend to several hundred meters. And I should clarify here that I'm not talking about the range of the BLE peripherals, like your wireless headset, Bluetooth headset. That should stop functioning after a few tenths of meters, right? But what I'm really talking about here is the range that the BLE advertising beacons can be detectable, especially in line of sight conditions. That's particularly dangerous. Now, I thought about calling for a show of hands to query about how many people have used the Google location history feature, a display of which you can see on this slide here on the map on the left. But we are virtual, so I'm going to guess that most of you are aware that the feature exists and is based on GPS data reception. And some of the early contact tracing implementations employ GPS data. I would say that apart from a gross violation of privacy, this is totally unnecessary for the contact tracing process. GPS coordinates are not accurate to the meter like the Bluetooth data, and at least not in civilian versions. Many authorities, of course, have tried to experiment a bit with density maps, trying to actually create maps of detected infections based on GPS coordinates. That's a totally different business. We are talking about the actual basics of the contact tracing process, and GPS coordinates are not good, I'm afraid. Continuing with the privacy aspects, it's obvious that collecting proximity and health status data massively, even if these data are anonymized in theory, is a sensitive issue. This is backed by evidence. So moving now to the central or distributed infrastructure bit for contact tracing beyond the smartphone device, it is imperative that we standardize the handling and usage of the collected data in approved and tested ways. And to do that, the EU, actually, the European Union, is a major player in that field. And since, I think, April 2020, they have published a set of recommendations that suggest ways to handle the data. For example, they place lots of limits on unencrypted data, on personal data. They limit the time. We can't store the data we collect for contact tracing forever. They, of course, mention explicitly data accuracy, which, surprise, surprise, is an issue for BLE. And they often also dictate data interoperability, which means a mechanism to make data interoperable across the entire EU area. But however, as time is of essence, when one has a formidable task to perform, it's useful to search for already existing paradigms that could be relevant to the task at hand. So genomic medicine is, in my honest opinion, one relevant paradigm because it has already best recipes for dealing with the security, the size, and effective distribution of sensitive health data. Some of these data are also anonymized, although depending on how one uses them, they could identify individuals and thus are susceptible to leakage attacks. So the European Genome Phenome Archive that you see here displayed on the left, it's a screenshot, is a good representation of infrastructure tailored for handling this kind of data. representing millions of man-hours dedicated to do this task. And another good example to back the fact that the COVID-19 data do represent sensitive data is to look at what current practice dictates. So the University of Oslo, which is the largest academic establishment in Norway, is the administrative host of the largest hospitals in the country, and it thus deals with a large number of sensitive data around the world. And as a result, the university employs a rather comprehensive data classification system that has, of course, invested in infrastructure to securely collect, process, and deal with this kind of data. A snapshot of this architecture you can see here. So we employ, for example, in an infrastructure called Tjenester for Sensitive Data, like services for sensitive data in Norwegian, a combination of technologies like two-factor authentication, firewall techniques, virtual machines to ensure that we compartmentalize the processing of data, and of course, plenty of storage and processing power to analyze the data. We could actually use contact tracing data for models, prediction models, but all of that is already done. So the big question here is why, when we have things in Europe like the EGA archive and the TSD, governments have actually went their own way, and they actually placed rather intransparently all this contact tracing data in their implementations in the cloud with no assurances and no auditing. So to conclude, all contact tracing infrastructures represent digital contact tracing infrastructures represent a huge challenge that needs an end-to-end expert review. So we start from the mobile phone, the application, and then we also audit the backend infrastructure. We need to take precautions for data locality. We have cases where data from Norway ended up in data centers in Ireland. And I'm not sure if this is totally legal, but it's definitely something that should be looked at. And finally, when it comes to the BLE data accuracy, we need approved calibration standards. I would like to thank you. In the interest of time, I will stop here and take your questions.